All right, hello and welcome to another revisiting of Monte Carlo techniques in our advanced statistics course. So, revisiting what we talked about with Monte Carlo last time, boiling it down to its bare minimum, right? So that we can talk about it from a, well, what is it really, right? Uh, it's made up of basically these 3 to 4 things or 5 things, depending upon how you want to count. There's sampling with or without replacement, or potentially random number generation, which you could kind of view as being a form of sampling using loose terminology. And there's a loop. Generally, you go through it a certain number of times. Essentially, each time through, you're going to be taking a sample. You're going to apply some method, some model or function to that sample, and then save the results. And then you're going to do some aggregation across those results. I struggled a little bit with if the sampling should be at the beginning or inside of this loop function. And it can kind of be either way, but regardless, you're going to basically pull sets of samples and then do something on them. It is very similar to bootstrapping, except that it does include sampling, whereas a bootstrap sort of approach doesn't necessarily have sampling involved. So what I thought I would do today is work through some kind of detailed examples, starting off with essentially the central limit theorem. And also ties into the law of large numbers. So the basic idea is kind of intuitive, right? Is that as the sample size increases, the distribution of the mean across the multiple samples will approximate a Gaussian distribution, which is a normal distribution. Fancy terms, right? So it'll turn into a bell-shaped curve. The Gaussian distribution is just that. It's the normal distribution, or more specifically a function that delivers a Gaussian sort of number will result in a normal distribution if you apply enough values to it, right? It's assumed that you're going to marry or measure those values, and eventually it's coming down to essentially a normal distribution. So that's the basic idea of central limit theorem and the Gaussian functions. Where's my tab? Okay, here we go. So I took this example from a book that's available inside of the O'Reilly set you have, which is hands-on simulation. Pretty good book, and it's available to you as part of going to this university, so might want to take a look at it. Pretty cool stuff. There's a lot of good stuff inside of this O'Reilly repository, so I strongly recommend it to you. So most of these books will have also a GitHub repository that you can then pull the code examples from the book. What I've done here is taken that, made it prettier, cleaned it up. It's their stuff. I didn't write this stuff, but I did make it to where it's maybe a little more interesting. So we start off, and I kind of commingled it, making it kind of a living book, if you will. So I start off with the typical imports that you always do: random, numpy, and plotly, or pyplot to go into as an alias with plot. Typical sort of stuff. So start off with, we kind of need to understand the central limit theorem, and that's basically what we just talked about. And the reason you might do Monte Carlo is that sometimes you can't easily get the direct calculation. So instead, and that's a recurring theme with Monte Carlo, is it's the next best thing, right? If you can't do the actual thing, then you can approximate it with Monte Carlo. And the reason that it's acceptable is that the approximation is, generally speaking, pretty good. So that's something to consider. There's also this concept of the law of large numbers, and it's intuitive as well. The more you sample, the better your approximation will become. The more closely you're going to approach the real value. That's assuming that your functions and such are appropriate. So if you basically are approximating the number of coin flips, if you only do 10 of them and you get 4, then it's because it just happened to be that's what the randomness occurred. Then you're only at 40% when you actually know that intuitively if it's a fair coin that it's going to be 50. If you do it 100 times, you're getting a little better, a little closer to the actual approximation. You do 1,000 times, you're getting closer yet. Probably if you do it 1,000,000, you'll be close enough that it won't matter. And so that's one of the key concepts, is that generally speaking, the more that you roll those dice, the better that you're going to determine the actual values. And we'll skim through some of this, but this is basically a way of kind of showing that idea of taking something that is to be a normal distribution, and you're basically taking a look at it over checking to see that these things are all at the same level, right? And you can see there's a bit of things that are off, and that's because we did this for 10,000 times. If you take it and make that bigger, make the n bigger, so take it up to 1,000,000 times, right, you're going to end up with something that's most closer to approximating the real thing. So that's one thing to think about, and I'll go ahead and run these so that the values are present in case we need them later on, which I think we do. So here's where we get to that Gaussian distribution, right? So you can see there pretty much a bell curve, and it's doing that by essentially going through and extracting the mean from looping through this larger data value that we created up here with 1,000,000 records. And this is the same basic thing with 1,000, the original 10,000 or whatever it was samples here, right? So you can see they do approach Gaussian distribution. It's kind of hard to tell. This looks a little skewed, so maybe something up with what I'm doing to it probably would make it look better. So that's the basic idea of this central limit theorem, is that in combination with the law of large numbers, the more samples, the better. And this is what, when we talk about the elements that make up a Monte Carlo sort of experiment, you have sampling going on, you have a loop going on, you're extracting or calculating some measure and saving it here. So we're determining a mean, we're saving it, and then after the fact we're doing something typically with that. In this case we're just plotting it, but that's the basic pieces of that puzzle, just as I mentioned, those 4 or 5 things that go together to make it be Monte Carlo. And it's not there's a lot of complicated words in some of this stuff, but it's not necessarily all that hard. And again, the whole point of doing Monte Carlo is because you can approximate a system that may be too complicated to measure directly. And that's the reoccurring theme here. So moving back to our next thing, integration, and doing it from a numerical perspective. So recall from back in calculus or pre-calculus, way back whenever you, probably in high school even, you can do integration to get the area underneath of a curve between 2 points. That turns out to be quite useful if you're wanting to measure that area. It could be that you're wanting to do it as a way of determining potentially the volume of error that's occurring. That's one thing you might do with area under the curve. So that's one of the key concepts, is you do an integral to do that. And integration and all that good stuff, yeah, that's not this class. But we'll go over it briefly, and I'll keep it and kind of probably skim over some of the math, right? Again, this is from a nice book that's available to you, Hands-on Simulation Modeling with Python. And chapter 4 talks about Monte Carlo, and that's where we're pulling this one from. So when we talk about integration, there's times you can't necessarily do it the mathematical way, and so that's where you're going to use a numeric integration and using Monte Carlo to do that. And so that's basically a way of approximating the integral. So lots of fun stuff. If you remember, this is the basic thing. You're integrating from a to b of some function that is essentially a derivative of x. And then there's a range, right? So we figure out kind of the start and the begin, and we basically figure out that there's a box here, right? So again, similar in a way to the needle drop experiment with approximating pi we talked about last week, right? It's you come up with a bounded region. Inside of that region, you have some discriminant function that allows you to determine if something's in or out of the range that you're interested in, and then you figure out what that ratio is to come up with the variable thing. So another interesting thing, just as an aside, this is a Jupyter notebook, obviously. So you can see Jupyter up here and so on, right? And the environment it's running in. I spent a fair amount of time importing, and this image is actually coming straight off of the place, this chapter. So I'm actually referencing the image. And if you're interested, this is the syntax you use in Markdown, and this is a nice way of making your output look very, very compelling, right? So you're actually showing this is the function, and all you have to have is a public address for that to work. So it's a nice kind of way of doing that. You could put it out on your own GitHub account or whatever it might be, and make it accessible through the browser. So the basic idea here is that we're approximating the area underneath this curve by bounding it as a box so that we do essentially the in and out of that region sort of calculation. And we come up with a function to where we can figure out if it's in or outside of that configuration. Then we calculate essentially the number of hits minus or divided by the number of misses, so to speak, or the overall number. So the number that were in the region and the ones that were out, and come up with the formula so that we can then determine the integral approximated by that formula. So the numeric solution allows us to run something with a Monte Carlo approach in an iterative fashion that can approximate something that might be challenging to produce normally. This particular example, not all that complicated, and if you can brush off a few cobwebs, you could probably do the integral. But it is quite interesting as a simple example of showing how Monte Carlo can be very powerful. So whenever we initialize the random number generator, we do it with a seed. What that does is make it reproducible. If you leave it to where it's random, probably it's going to grab like the tick count off the processor or something, so that each time you run it, you'll get different results. By setting it to a constant, not all that great from a real mathematical perspective, but pretty good from a demo perspective, right? Because if I run this thing twice, I'll get the same answers. This also introduces the concept of a lambda function. In this case, we're squaring a function. So this is the same thing as a name function that just took a parameter, multiplied it by itself, or squared it, and then returned the result. But this is an anonymous function. It doesn't have to have a name, so we can basically just refer to it as f, which is nice because we talk about f of x, right? So this is a simple way of having an f of x. And this sets up that lambda function for us to use. Pretty cool. Anonymous functions are a cool thing to use. And next we talk about coming up with the region from 0 to 3, and then we talk about how many steps we're going to do. So this is the bounding region, right? A and B represents the range that we're going to calculate the integral. Back up here at the top, when we have this integration from A to B, that's the A and B. The other value is the number of loop or iterations in the loop, right? So we're going to run for 1 million times. There was a time that 1 million times would be a big deal, right? Now processors don't hardly break a sweat running through it. We also set up 4 vectors to catch things that are going to be inside of the integrals region, or going to be outside of it, but still inside of the rectangle. So again, very similar to what we did with the approximation of pi. And so all we're doing here is initializing it to an empty set. We set those values from 0 to 3 and say we're going to run 1 million times. Then the next thing is about figuring out if it's inside of that region. So that's where this f of x comes to play. And it's all about figuring out what's the minimum and the maximum of the function and so on. The basic code, jumping straight into it because this is a class about writing code, is we determined that initially that the y min is the f of x, right, of a. So we start at the essentially leftmost region of our region that we're trying to integrate across, and then we loop for 1 million times, right? So num steps is 1 million. And this is just basically going in the range of 0 to a million. And we calculate x to be a plus b minus a times the float of I divided by the num steps. So basically we're doing a gradient of our current little slice of that from 1 to a million and the range of a to b, right? So it's the width of b minus a, so that width of the box that we're interested in, and we're starting at a, and then it's just basically turning the I into a float. So we're running from essentially 1 to a million, dividing it by a million, right? So tiny little slices. And then we're calculating for each one of those the y of f of x. So we're determining if it's what the value is. So we're essentially squaring y. And then if it's y is less than y min, then we get a new min. If y is greater than y max, then we get a new max. So typical sort of processing. Go ahead and run that, and you can see a million, nothing to sneeze, just rat over it, right? Didn't take any time to speak of. So now then we need to do some calculations about big A, which is b minus a times y max minus min. And then again, n is the number of random points that we're doing. We probably don't really need to set it again because it's the same, but it does make it clear because m is the number of points that fall under the curve, right? Represented by f of x. So we run through again another loop. This time the first pass through was figuring out what min and maxes are of f of x, right? So that's what that's basically doing, is figuring out how big it goes and how little it goes. And you're probably making some assumption here of about cycles, although that may not matter too much. So now we're running through. We know what min and max are. We're picking random locations of for x and y. So we're basically throwing a bunch of darts or shooting a bunch of bullets, however you want to think about it. And then we're checking to see if y is less than or equal to f of x. If it is, then both x and y fall in that area of a that we're interested in. Otherwise, it's outside, so it's outside of the integral. We're also saving each one of the x and y's here so we can plot it later on. And so we'll go ahead and let that one run. And again, really fast, right? So now to do the actual numeric integration, it's as simple as m divided by n times a, and it'll come out to be 8.996787, right? And the real answer is 9 if you actually do the integration. It's going to be x cubed divided by 3, so in the case of, what was it, 3, so 3 cubed, 27 divided by 3 is 9. I'm going to have to pause for 1 second. All right, apologies for that. I had an ill dog I had to deal with. Seizures, which is concerning. Back to numeric integration. So we can calculate here that the error is really pretty small. That's 0.03%, and we could probably make it even smaller by increasing the size of n, so that we actually essentially roll the dice more frequently. So to take a look at the visual representation, we can actually plot it so that we start off by constructing some lines, and what we're interested in is plotting f of x, basically. So that's what this is doing, is determining f of x and saving for all x's what is in the range of a to b, what is the values of x or of y. And so then we can turn around and plot that, and we can see it's a nice little line going from 0, 0 up to 3, and ideally here at 1 should be 1, and 2 should be 4, right? So that's kind of what we know about square root or squared. Then we probably want to take a look at plotting what is inside of the box, or the integral, and what is not inside of the integral but inside of the box. And so we'll do things that are inside of the integral in blue, under the curve of that line, right? That's what we're talking about. And things above the line are in yellow or outside of the integral. And so you can see nice little line showing that it is nicely scattered across. Takes a little bit of time to plot, but that's because there's quite a few points. And you can see by the smoothness of the line very clearly demonstrates it. So that's numerical integration. Again, not exactly 100%, but sometimes 3% error, or was it 0.03% error? 0.03% error is close enough, right? And that's where these sort of capabilities come to play, is whenever you can't do the real thing, so you approximate it, but the approximation is really close. Shifting back in. Talk about some demos in R. So far I've been a little biased in my presentations of lots of Python, not so much R. So we'll go through it and do the pi version of the Buffon or Buffon, or however you would say it, method of approximating pi. So shifting back over to that. Close this. Oh, come on. And we're in some sort of loop. There we go. All right. Not sure why I did that. So, okay. Again, taken from a book out of O'Reilly. In this case, the handbook in Monte Carlo simulations and focused in on financial engineering, risk management, and economics. Some pretty good examples in here as well. So digging into it, this actually talks a bit about the history, and I went ahead to the trouble of kind of reproducing the contents of that chapter here because it is a nice sort of exercise to understand kind of how it came to be. We don't necessarily have to get into all the math, but the end result is you end up with a function to where pi hat is basically 2 ln over th, right? And so that basically gives you a function that can then be expressed in terms of what does h look like. And it turns out to be basically x squared plus y squared is less than 1 is the basic idea. And again, we're dealing with and that's this formula up here, we're dealing with a unit circle. So the circle is got a diameter, I believe, or radius of 1. So the area is going to be the square of pi over 4, right? So that's the basic idea, and that's where this comes in. So the programming for this one is much simpler in some ways, but there's probably a way to do the same thing inside of say NumPy, I would assume. So we basically go off and do the runif, which is run, or runif is probably the better way to say that, because it's the random uniform distribution calculation or generation. So we're generating a random distribution of n items for both of these cases, and then we're multiplying them by 2 minus 1 to give us our y's and our x's, and then we calculate h as the sum of those, x squared plus y squared over is less than or equal to 1, and that gives us back and then 4 times h over n, and that gives you pi. It's that simple. And so here you can see the approximation pretty quick on the 1,000, and then as we make it much bigger, I believe this one is the 100,000, or no, this is. So we can see that at the point you do it a bunch, you get a pretty good approximation, and a bit simpler of a set of code, perhaps, right? Although from a purist perspective, I don't particularly like it because you don't see the loop, but the loop is in there. It's inside of here, right? And then you're doing some matrix, essentially set-wise manipulation to produce this. So certainly, yeah, it's at a set level versus a straight-up iteration, but it is doing it internally, so you're just not seeing it. Perhaps a bit more efficient as well. And then this gives kind of the examples of what's going on with that R unif, right? And it is a normal distribution across the number of n items that we asked for. From between the ranges of 0 and 1. So that's the simplest version of calculating pi. Shipping back, so we did pi auto regression, right? Recall that's a way of kind of finding a solution or doing regression essentially against a single variable. It's a simple model of auto regression. So this is basically working through a similar sort of experience where you're calculating and approximating a regression in an iterative fashion. Again, pretty much similar sort of concept in this. This is the pattern that this author used. I kind of restructured it so it's easier to see, but they define a function, in this case AR for autoregression, that has all of the logic in it, and then they basically just call it from something else so that you can kind of fiddle with the variables or the parameters without changing the actual code. And this one does at least contain the loop, right? So you are seeing it loop through and calculating the formula up here that we see. So mu plus a times x sub t with a r norm from 1 to 0, or from with 1 to sigma range, right? So whatever sigma is, the max value of whatever we pass in. So in this case 1. And so that's basically it. Then it essentially is plotting it, right? So we're plotting those lines so we can see it approximating the regression. So kind of interesting, kind of cool. Geometric Brownian motion as well. Similar sort of concept, right? We set it up with a formula, and then we basically, inside of it, there's a couple nested loops. So you have the overall number of repetitions or iterations, and then inside of that you've got a series of steps that start and basically are going through a matrix, right? And then the idea being to essentially plot the shape of that across two different values, one being 10%, one being 40%. So fairly useful, meets all the characteristics we talked about, doing something inside of the loop and saving it. So we're saving it into, essentially in this case, a matrix. And that's what we're basically doing here, is we're iterating through these two different things so we can assign a value to each one of these based upon the combination. And there should be some sampling, if not sampling, some random number generation inside of here. And so that's the basic characteristics of a Monte Carlo simulation. And then this next topic is talking about discrete event single queue simulation of a queuing system. Basically, there's a type of Kendall notation, it's what it's called, and you may see this, you may not. If you're doing simulations, you'll see it, and it's MM1 is what you would say, and that's basically saying that the arrival is essentially random. It's Markovian. The service time is also random, and there's a single server. That's what the 1 is. So things are coming in randomly, they're being processed in a random time, and they are being served by a single thing. So an example of this might be a bank teller. So you have random numbers of customers coming in, so they come at a random interval. You have a random amount of time each transaction takes, because not everything is uniform, so it's essentially random with some sort of distribution. And then there's only, say in this case of a one queue or one service thing, you've got one teller on duty, right? So multiple randomness coming in. You don't know exactly how many or what that distribution looks like, but it's the way of defining what it means. And generally speaking, there's a first in, first out queue. So you're queuing up like you would normally at a bank, right? And that's the basic idea. And this is a fairly common thing to do and you can talk about it in terms of like the depth of the queue. So how many people were in line? Initially none, so this is across time. Then there's one in line for a period, which is kind of interesting because you would think they would go straight to the server. And that's one of the things that you may have to, when you're doing this sort of thing, make sure that your simulation is complex enough, right? And the reason you would do these sort of simulations, the whole point of this is you want to maybe based upon historical information, you can capture the arrival times of your customers on typical days of the week, and you might want to adjust your staffing so that their average wait time is under some threshold, because you know at some level they'll do something called balking, which basically means they've waited long enough and they're out of there, right? These sort of patterns are common across lots of different usages, and it's a good way if you can come up with essentially the formula that approximates, or a model that approximates the customer's behavior, or whatever it is you're modeling's behavior. You can then do things like adjust how many servers are working at a given point in time. That's the whole point, is to minimize cost while maximizing customer efficiency and safety, or satisfaction. So that gives you an idea of roughly what it could look like. And so we come up with essentially some utilization rate and come up with the functions to determine what their wait times is going to look like. And it's basically going to be a product of a given user's wait time is the time from the point that they enter the queue until they exit the queue, plus the potentially the transaction time of and so on. So you've got an overall time that you can calculate. So again, using a function, we pass in a lambda, a mu, and how many. We calculate a fixed array, and that's what this a pre-allocated array of W elements. That's what this is, or of how many elements. And then you have the ability to set some obviously default values, and that's what these are doing. So that syntax is setting some defaults so that you only have to apply or send in the ones that you care about. The RXP is a exponential distribution, and the rate at which it is going is a mixture of lambda and mu, and then the maximum wait time of a given individual is the serve time minus an initial time, so whenever they first came into the queue and how long it is until they're served, and then plus essentially the people before them, right, or the person before them. And so with all that said, you can come up with an approximation of the wait time, and you can do so that you can try a certain utilization rate, right, of 90.9, right, a product of mu there, or you can change to a 50% wait time, or essentially utilization rate, and you can see the wait time is significantly smaller because you're not utilizing your resources as much. So that's the trade-off, right, of any sort of simulation. And the point of doing those simulations is to be able to determine the relationship between how long how much utilization, how many resources you're having to put at it versus what's the benefit you're getting out of it, and finding that break-even point, because there's probably a certain wait time that beyond which almost no one will stay in line, right? So there may be a few people that once they're in line they stick to it, but there's a lot of people that only have so long to do certain transactions. And so with that, we've covered off this queue modeling approach. I'm going to skip over this, although this is basically to demonstrate that sometimes you're dealing with topologies that finding through just iteration a minimum or maximum can be quite challenging. And this is showing it to us in a 3D-ish sort of view, and also in a topographical sort of view, right? Obviously artificial looking, but it can make it very hard for a discriminant function to figure out how to find essentially like a local minimum or a local maximum. So that's one of the things where those come to play. So moving on, these are kind of interesting with some of the pitfalls of Monte Carlo simulation. So things that can go badly. sometimes you want to make sure that you have a large enough sample so that you're pulling an appropriate sample size. So you want to make sure that whenever you're sampling your data, that the data you're sampling from in a random way is large enough so that you're not messing up your calculations. Also, this is an example that there's additional elements that go into simulations with queues. There's oftentimes like a spin up time or a startup time. There's also potentially breaks that the queue servers may need to take. Lots of things can go on. There's good examples of some things that can happen that throw things off. We want to be cautious when we're doing it. Make sure that it's being applied appropriately. That I can shift back. And then revisiting integration from an R perspective, right? Similar sort of concept, but again, taking a much more, not so much iteration approach, but a more of a what would you call a set-based approach, right? And this is taken from the blog up here, right? So again, it's okay to use different resources to sample things and so on, but just make sure that you explain. And this is basically talking about the same sort of thing we went through in detail, but it's now showing it in a much simpler way, right? Because we're basically creating a normal distribution with a standard deviation of 10 and a mean of 1, and we're doing so, whatever that is, 100,000 times. So it's exactly what this is doing, and it's giving us back our answer. Similar sort of approach of approximating pi. This time we're using a full circle rather than a quarter of a circle, but it's the same basic concept. So you generate again a uniform distribution, and in the range of -1 to +1, so 0 in the middle of the circle. So again, a unit circle, but centered on 0 rather than centered somewhere else. And then basically a calculation that it's in the circle if it's that basically x squared y squared is less than half squared. So basic sort of calculation. And then you can figure out pi by summing those things up, dividing by the number of lines, and then multiplying it by 4 to get the 4 quadrants essentially. And then here we're basically coloring it in with the dots. So if you were to increase this a bit more, you would get a more complete set of dots and a better approximation, right? And then take it out another level and it would even hopefully get better. And so that's the nature of these sort of things. Is obviously the more you run, the better, but the longer you run can get to where the runs themselves take so long that they become prohibitive. So this is the trade-offs that you consider whenever you're doing Monte Carlo simulations. Again, the same, the basic looping is happening more by the generation of the data sets, and you can see as we increase that number, we get a better approximation and a more thorough sampling, and more things are filled in. So pretty cool stuff. And with that, we've talked about pretty much everything I have. So as always, if you have any questions about the material that I've covered, feel free to reach out to me. That's what I'm here for. I want to make sure that this is both covering off the theoretical elements and also covering off the application elements. Again, to summarize again, the whole point of Monte Carlo is it's what you do when it's what you can do. So it is approximations, but sometimes those approximations are close enough. Sometimes you're approximating systems that are very complex and can't be expressed in some other fashion. So you may take something like the historical arrival times and service times of some sort of scenario, be it manufacturing, banking, customer service in a retail situation, fast food, whatever, and then come up with approximate staffing models perhaps, or it could be delivery mechanisms of materials used to manufacture things based upon demand. And you come up with some sort of optimization, and that's the whole point typically, to figure out roughly what it is you think you'll need on average. Now, as with anything, there are unknown events, right? So if you're doing something like trying to look at seasonal trends of air traffic flying, something like 9/11 would totally throw that off, right? So there are exceptional events that occur in any of this stuff, so we can't foresee those. But for some things, we can approximate them using things like Monte Carlo as an example. So this next Thursday, we'll be talking about Markov chains. I did run across an article or a text that was talking about the combination of Markov chains and Monte Carlo. Kind of interesting, but a little bit of an advanced topic. So I may or may not be able to run that in on our next Monday call, but let me know if that sounds like something of interest. The Markov chains are pretty cool. It's all about state transition diagrams and raising matrices to power. So cool stuff. So with that, I'll wrap this up. Again, if you have any questions, let me know. Stay safe, and we'll talk again soon.